For decades, one of the largest star clusters orbiting our galaxy has been keeping a secret that flat out shouldn't have been possible to keep. Models say it should be packed with roughly 10,000 black holes. Actual observations found essentially zero. That gap sat unresolved for so long that some astronomers started wondering if something was fundamentally wrong with the models themselves. Then, using 20 years of archived images nobody had fully mined for exactly this purpose, researchers finally found one. Stick around, because I'm going to walk you through exactly what Hubble and Webb just confirmed about Omega Centauri's missing black holes, why finding just a single one required more than 2 decades of patient data collection, and why this particular black hole turned out to be even stranger than researchers expected once they actually found it. And if you want more of these deep dives into real published research, instead of recycled headlines, go ahead and subscribe now, because there's a lot more coming out of the search for the universe's hidden black holes. To understand why this discovery matters so much, you first need to understand what Omega Centauri actually is, and why astronomers expected it to be full of black holes in the first place. Omega Centauri is a globular cluster, a densely packed, roughly spherical collection of stars, all gravitationally bound together and orbiting a common center. It's the largest and most massive globular cluster orbiting our own Milky Way, containing an estimated 10 million stars packed into a relatively compact region of space. And it's also among the oldest structures in our galaxy, meaning the stars within it have had billions of years to live out their entire life cycles. That age and stellar density matter enormously for this specific mystery. Massive stars, considerably larger than our own sun, don't simply fade out peacefully at the end of their lives. They explode as supernovae. And when a sufficiently massive star explodes, what's left behind after the explosion can collapse under its own gravity into a black hole, an object so dense that not even light can escape its gravitational pull. Given how many stars Omega Centauri contains, and given how old the cluster is, meaning plenty of time for its most massive original stars to have already lived, died, and left black holes behind, astronomers have long calculated that the cluster should be genuinely swarming with these objects, home to something in the range of 10,000 individual stellar mass black holes, each one formed from the death of an earlier massive star. If you're finding this as fascinating as the researchers involved clearly do, drop a comment and let me know, because it genuinely helps me figure out what other space stories are worth covering next. The problem, for decades, was that none of those predicted black holes ever actually showed up in observations. Astronomers had already found compelling evidence for a different kind of black hole hiding at the very center of Omega Centauri, a so-called intermediate mass black hole weighing in at a minimum of roughly 8,200 times the mass of our Sun, confirmed back in 2024 by a research team led by astronomer Maximilian Heberle, using more than 500 archived Hubble images to track 7 unusually fast-moving stars near the cluster's core. That was a genuinely significant discovery in its own right, but it addressed an entirely different part of the puzzle. It said nothing about the thousands of smaller, ordinary stellar mass black holes models insisted should also be scattered throughout the rest of the cluster. The reason those smaller black holes remained so stubbornly invisible comes down to how astronomers typically go about detecting a black hole in the first place. Most confirmed black holes get discovered because they're actively pulling in and consuming nearby material. Gas and dust falling toward the black hole heats up dramatically as it spirals inward, producing bright, detectable X-ray or radio emissions that telescopes can pick up from enormous distances. That method works well for actively feeding black holes, but it's completely useless for a black hole that isn't currently pulling. In any nearby material, what astronomers call a quiet or dormant black hole. A black hole like that produces no light, no X-rays, nothing at all for a telescope to directly detect, making it essentially invisible using every conventional search method astronomers have relied on for decades. If most of Omega Centauri's predicted 10,000 black holes happen to be quiet rather than actively feeding, which statistically most of them likely are, traditional detection methods were never going to find them no matter how long or how carefully researchers kept looking. The breakthrough came from switching to a completely different technique, one that doesn't require the black hole itself to be doing anything detectable at all: astrometry, the precise measurement of small changes in a star's position over time, offers a way around the entire problem. If a visible star happens to be gravitationally orbiting an invisible companion, that companion's gravity will cause the visible star to wobble very slightly in a predictable, periodic pattern as it moves through its orbit. Measure that wobble precisely enough, and you can calculate the mass of whatever invisible object is causing it, even if that object emits absolutely no detectable light of its own. To appreciate just how demanding that measurement actually is, it helps to understand the physical scale involved. Omega Centauri sits roughly 18,000 light-years from Earth, meaning any star within it appears as an impossibly tiny point of light from our vantage point. And the gravitational wobble astronomers were trying to detect represents a shift in that star's apparent position amounting to a tiny fraction of a single pixel on Hubble's camera, sustained and tracked consistently across more than 2 decades of separate observing sessions. Achieving that level of precision requires not just an exceptionally stable telescope, but an enormous amount of patient, methodical data processing, carefully accounting for anything else that could conceivably explain a shift that small, before researchers can confidently attribute it to an orbiting black hole rather than any other, more mundane source of measurement noise. That's exactly the approach taken by a research team led by Matthew Whitaker, an undergraduate research assistant at the University of Utah, working alongside Haberle and other collaborators. The team combed through more than 20 years of archived Hubble images of Omega Centauri, tracking the precise position of individual stars across that entire 2-decade span, looking for exactly this kind of telltale gravitational wobble. They found it in one specific star, whose position shifted in a smooth periodic pattern that could only be explained by an unseen companion with enough mass to be a black hole. To confirm and sharpen that finding, the team then incorporated more recent observations from the James Webb Space Telescope, using Webb's own precision to refine the measurement and rule out alternative explanations. The results, published on July 13, 2026, in the astrophysical journal Letters, confirmed the discovery. The object, formally designated oMEGACat BH2, is the first genuine stellar mass black hole ever confirmed within Omega Centauri. Once researchers had confirmed the black hole was actually there, its specific properties turned out to be almost as interesting as the discovery itself. oMEGACat BH2 has a mass of roughly 4.46 times that of our Sun, and that specific number matters far more than it might initially seem. Astrophysicists studying black holes, formed through supernova explosions, have identified what's sometimes called a lower mass gap, a specific range of masses, roughly between about 2 and 5 times the mass of the Sun, where black holes appear to be genuinely rare throughout the universe. Gravitational wave observatories like LIGO have spent roughly a decade detecting merging black holes across the galaxy and beyond, and objects falling within that specific mass range have come up conspicuously, almost suspiciously absent from that entire body of data. oMEGACat BH2, sitting right at 446 solar masses, lands almost precisely inside that theoretically underpopulated gap, making it a genuinely valuable data point for a completely separate area of astrophysics that had nothing to do with the original missing black hole mystery this search was trying to solve. There's a second unusual property to this specific black hole system that's generated just as much attention among researchers. The visible companion star orbiting oMEGACat BH2 takes approximately 94 years to complete a single orbit, making this the longest orbital period ever recorded for any confirmed black hole binary system. Nearly every other black hole binary astronomers have previously studied orbits its companion star considerably faster, often completing an orbit in a matter of days, or at most a few years, simply because those tighter, faster orbits are the ones that produce detectable X-ray emissions or gravitational wave signals in the first place. A black hole and companion star locked into a lazy 94-year orbit would never have shown up using any of the conventional detection methods astronomers have relied on for decades, which helps explain, in a very direct way, exactly why this specific object managed to stay hidden for so long, despite sitting in one of the most heavily studied star clusters in the entire galaxy. It's worth pausing to explain why this particular combination of properties makes the discovery so scientifically valuable, beyond simply resolving decades of frustration. Haberle, discussing the broader significance of this find, specifically highlighted what he called the immense legacy value of the Hubble Space Telescope's archive, noting that this discovery represents the second major breakthrough to emerge from the same ongoing astrometric reanalysis project, following directly on the heels of the 2024 intermediate mass black hole confirmation. Both discoveries came from mining decades-old Hubble images using techniques and levels of precision that simply weren't available when those images were originally captured, a pattern that's become increasingly common across modern astronomy, genuinely new discoveries emerging from data that's been sitting in an archive for years, waiting for the right analytical approach to finally unlock what it was quietly recording the entire time. This single confirmed black hole is also almost certainly just the beginning of a much larger search, rather than a conclusion in itself. Researchers involved in the project have explicitly stated they expect additional discoveries as Hubble and Webb continue surveying the cluster, using the same astrometric technique now that it's been proven to work. There's also a significant piece of future infrastructure specifically positioned to accelerate that search even further. NASA's planned Nancy Grace Roman Space Telescope, expected to begin operations in the coming years, is designed to repeatedly image crowded stellar fields with resolution comparable to Hubble's, but across a dramatically wider field of view, allowing researchers to track the positions of vastly more stars simultaneously than Hubble's narrower field ever allowed. Given that this entire discovery relied on patiently tracking one star's subtle wobble across 2 decades of data, an instrument capable of monitoring enormous numbers of stars at once rather than one at a time could dramatically compress how long it takes to find the next black hole and the one after that out of the roughly 10,000 still theoretically waiting to be discovered within this single cluster. So what does all of this actually add up to? A star cluster that has puzzled astronomers for decades, predicted by every reasonable model to be teeming with thousands of black holes, but stubbornly refusing to show direct evidence for even one of them, finally gave up its first confirmed example. Not through any dramatic new observation, but through 20 patient years of tracking one star's subtle gravitational wobble across an archive of images originally collected for entirely different scientific purposes. That single confirmed black hole turned out to carry 2 genuinely unusual properties of its own: a mass sitting almost perfectly inside a gap. Gravitational wave astronomers have been puzzling over separately, and an orbital period so unusually long it helps explain exactly why this entire hidden population managed to stay concealed for as long as it did. If stories like this one, grounded in real published research rather than exaggerated headlines, are what you want more of, subscribe to this channel and turn on notifications, because researchers have every reason to believe this is only the first of thousands still, waiting to be found, and there's a real chance the next one turns up even stranger than this one already has. Thanks for watching, and I'll see you in the next one.